Hi, welcome to Lambda U. My name is Andy and I'm a Solutions and Support Scientist at LICOR. In this course, we're going to be discussing the science behind the detection of near-infrared Western blot signals. We'll also cover the option for stripping and reprobing the blot, and we'll finally go over some optimization and troubleshooting tips. Afterwards, my colleague Jessica will go over some advice for best practices, and lastly, Sally will show you how it's all done in the lab. With all of these tips, you'll soon be an expert in near-infrared Western blot detection. So you've completed the final washes following the secondary antibody incubation step and are ready to detect your signals. At this point, let's take a look at how near-infrared fluorescent detection works in greater detail. As discussed in our earlier courses, blocking the membrane and secondary antibody incubation, our detection antibody is labelled with a fluorophore, also known as a dye. In order to get a signal that we can detect, we have to use a light source to excite that dye. The three typical light sources that we can use to serve this purpose are white light bulbs, light-emitting diodes, known as LEDs, and lasers. Every fluorophore has a particular wavelength at which it is most strongly excited, and another wavelength at which it most strongly emits light. These wavelengths are often referred to as the peak excitation and peak emission wavelengths, or peak XM for short. We want our light source to powerfully excite the dye at its peak excitation wavelength, but not to bleed over into the spectrum of wavelengths which is emitted by the dye, because this will be picked up by the detector. If this happens, this is referred to as light leakage, and this can negatively impact on the signal-to-noise ratio and therefore the sensitivity of the assay, since the excitation light would be wrongly captured in addition to the emitted signals. White light sources and LEDs both emit a relatively wide spectrum of wavelengths of light. In both of these cases, particularly with white light sources, the emitted spectrum has to be filtered, so that only the desired wavelengths reach the dye. This reduces optical power and therefore the strength at which the dye is excited. And even with this filtration, some light leakage will still occur. These two factors combine to lead to suboptimal signal-to-noise ratios. Lasers, on the other hand, emit a very narrow spectrum of wavelengths of light, and therefore light leakage is eliminated and the dye is powerfully excited, which greatly improves signal-to-noise ratios and therefore gives us better sensitivity. As we mentioned, when a dye is excited, it gives off light at a slightly different wavelength to that which was used for excitation. This emitted light signal can then be measured using an appropriate detector. There are two main methods for detecting the emitted fluorescence: CCD imagers, known as camera systems, and laser scanners. These capture your signals in different ways, so we would encourage you to learn more about how your system works, maybe from your lab manager or the instrument manufacturer, for a better understanding. If you don't yet have an imaging system, you can consult a LICOR expert for advice. Regardless of your choice of imaging system, the protocol for detection remains broadly the same. After the final wash in either TBST or PBST, you should rinse the membrane in pure TBS or PBS to remove the excess detergent, because detergent fluoresces and could cause unnecessary background. You can then choose to image the blot as it is, wet in the buffer, or to dry the membrane completely prior to imaging. This choice depends on several factors. Imaging the blot wet is the fastest way to get your data. Simply place the wet blot directly into the imaging system with a slight excess of buffer to make sure it doesn't dry out during the imaging process and making sure that there are no air bubbles, and then acquire your image. However, drying a near-infrared Western blot provides a number of advantages. First and foremost among these is that drying the membrane tends to lead to an increase in the signal-to-noise ratio, and therefore better overall sensitivity of detection, which will help you to observe weaker signals. It's also easier to handle, transport, and store a dried Western blot. Fully processed near-infrared Western blot membranes can be stored in the dark at room temperature for several months, and re-imaged or even reprobed at a later date. This can help you to keep a physical archive of your blots as well as a digital archive of your data, which can be especially useful if a reviewer ever asks you to re-image a blot. LICOR's Western blot storage bags are the ideal solution for storing your blots. You should test both wet and dry imaging to see which works best for your particular blots. Drying the membrane usually yields the best results, but not always. If you happen to have quite a high background on your blots, then drying can actually sometimes reduce the signal-to-noise ratio, so make sure to try it both ways. However, blots should not be dried if you plan on stripping and reprobing the membrane. Drying the blot greatly increases the strength of the bonds between the antibodies, the proteins, and the membrane, making stripping the antibodies much harder. If you do intend to strip the blot, make sure to do this while the blot is still wet. You can then dry it out and store it to be reprobed later. We talked about how to dry your blots in the earlier course, Drying the Membrane. There's a lot of useful information to be found in that course, but as a reminder of the basics, you can simply place your membrane between two pieces of filter paper and let it air dry for about 40 minutes to 1 hour, or longer if you want to pause your protocol. However, remember that we now have dye-conjugated secondary antibodies bound to the membrane, and the dyes themselves are sensitive to strong light sources, which can cause photobleaching, which is an irreversible reduction in the fluorescence of the dye. Because of this, it is important to keep the blot protected from light while it is being dried or stored. So make sure to keep it in a light-tight container or covered over with foil as a minimum. Later, Jessica will guide you through the best practices for imaging your blots, whether they are wet or dry. But first, in the next couple of lessons, we'll discuss the science of stripping, reprobing, and re-imaging your membranes.